Hi, everyone. Thanks for joining in. I'm excited to welcome Sylvia Herbert. Sylvia is a professor of mechanical and aerospace engineering at UC San Diego. She was Claire Tomlin's student back in Berkeley. She's been working on reachability analysis for a few years now. If you're familiar with verification and validation in computer simulation, Sylvia's work is really important. I've been following her work for a while. She does interesting work in terms of scalability of HJ reachability for verifying autonomous systems. But I would say the applications of these algorithms are not limited to autonomous systems. If you're into computer verification or validation of dynamical systems in general, I would say this talk is going to be important. Um, I looked at all the papers at NeurIPS this year that had to do with autonomous systems, certifying safety for autonomous systems that I reviewed for. Basically, all of them cited research from her and people in our orbit. And so I feel that in the next few years, this research is going to be very consequential to topics like self-driving, safety analysis for physical systems and such. So yeah, I'm really honored to welcome you today, Sylvia. And with that said, please take it away. And by the way, she has mentioned that she would like to take questions at the end of the talk. But if you have clarifying questions, feel free to drop them in the chat, and she would like to respond there.
Yes, yeah. If you have any clarifying questions, I'm happy to address them quickly. I have a lot that I would like to cover, so if possible, saving the deeper ones for afterwards would be great.
Yeah.
Thank you so much for that warm introduction. I really appreciate it. Yeah, my name is Sylvia Herbert, and today I'd like to talk about safe real-world autonomy in uncertain and unstructured environments. Very quickly, this work is by no means just my own. I really love collaborations, and I have a really incredible list of people that I got to co-author with. So I just want to quickly put that out there first. Okay, so the motivation of this talk is pretty straightforward. It is just that we want our autonomous systems to operate safely in real-world environments. From the controls perspective, what this means historically is try to verify that every possible trajectory of your system is going to remain safe. And as we look at more and more complicated systems operating in more and more uncertain and unstructured environments, trying to enumerate every possible trajectory and validate safety of that becomes completely intractable. And so often we end up in industry instead taking these complicated systems and using heuristic measures to try to ensure safety. And this can work sometimes, but sometimes leads to disaster. So just a couple headlines that I pulled: driver says Tesla car gets confused and crashes on highway, and time to panic, a robot killed a factory worker. So there's a need of trying to bring the concepts of rigorous safety analysis to these more scalable applications. So my goal, therefore, is safe, scalable, and adaptive autonomy. And in addressing that, I'm going to talk about a few major thrusts that I've been working towards. One is just improving safety analysis, so improving the scalability of doing traditional safety analysis and being able to update those analyses in the face of changing and new information. Using this, we've been able to take systems that before were intractable and maybe do analysis on the order of hours, or ones that used to take hours and instead doing minutes or seconds, which is really exciting for me. But it still doesn't quite get us to the point of doing like real-time generation of safe control while navigating in an environment. And for that, we then move on to the second part, which will be safe decision-making in real time, using fast track, or fast and safe tracking. And this uses this fun game theoretic analysis in order to be able to plan very quickly with a low dimensional system with safety guarantees for the high dimensional system. And that algorithm and framework has been used now in multiple different universities and government labs. And then finally, everything that I will talk to up until this point will be essentially dealing with unknown environments, but unknown static environments, which is not very real world. And so when we deal with the fact that the environment will be moving, and sometimes moving in ways in which it's hard to predict ahead of time, like dealing with humans, how can we reason probabilistically using models of how humans move in order to reason about safety, and also reason about how confident we are in those models? Okay, So with that, let's start with the safety analysis part. And again, clarifying questions, please interrupt me or write in the chat. So first, I'm going to introduce just the standard safety analysis approach that I'm coming from, this Hamilton-Jacobi reachability analysis. Then I'm going to talk about two improvements that we've been working on. One is system decomposition, and the next is applying warm start analysis to this. So first, standard Hamilton-Jacobi reachability analysis. The idea here is that we do have some model of our system. So here we have a state that changes over time. It changes as a function of its current state, its control or action, the input to the system, and potentially some sort of disturbance that's being applied to the system. This disturbance could be like a real external disturbance, like wind kind of blowing against your aircraft or something like that. Or you could think of it as uncertainties in your system that you're treating as a disturbance. In both cases, we assume bounds on the input, the control, as well as the disturbance. The worst of the disturbance can affect your system. We then have in our state space some goal that we would like to reach in our environment and or an obstacle we'd like to avoid. Let's start with just a goal. And we'd like to compute what we call the reachable set. So the set of states for which I am guaranteed to be able to reach my goal despite worst case scenarios. So despite the wind blowing as hard as it can against me, I have a controller that tells me the optimal control to be able to reach my goal within the time frame that I care about. So to compute this, first we lift this up to a higher dimension and we define a cost function over this. So this cost function is pretty simple. We use a signed distance function, which means that we have negative cost inside of the goal. That's good, negative cost. And high cost, positive cost outside of the goal. And again, we just use typically a signed distance function for this. Using that cost function, we now want to define a value function. And this value function takes in some initial state and some initial time. And it's going to ask, given this initial state and initial time, I want to find the minimum cost of trajectories of the system starting from that state and time. The minimum cost, meaning the closest to that it ever gets to the goal. So if that minimum cost of a trajectory is negative, it has managed to reach the goal. If that minimum cost is always positive, then at no point in that trajectory was it able to reach the goal and attain negative cost. So we want to take the minimum over time of cost of our trajectories. Here I'm going to go ahead and input our trajectory notation. And now there's just one more step to our value function. We actually don't have to enumerate every single possible trajectory. It's sufficient to look at the optimal trajectories. So to say, if I'm doing my best to try to minimize the cost, and I assume that the disturbance is doing the opposite, it's trying to maximize the cost and work against me, when will I be able to reach a negative cost? And so here I'm going to throw in an inf soup where I'm trying to minimize over control and maximize over disturbance. So this is our value function. If I put in a particular initial state and time, and this spits out a negative number, that means that over the time horizon, that initial state and time will be able to reach inside of the goal. If that number is always positive, then it will never be able to reach inside that goal. It's very valuable to have the value function. Sorry, I didn't mean to do that. But constructing this value function is not always straightforward. This optimization function can be pretty complicated, especially for general nonlinear systems. And so the general approach to solving this is brute force dynamic programming. And so to do this, we have an update equation. We call this the Hamilton-Jacobi-Isaacs PDE. You can think of this as a fancy continuous time version of the Bellman equation, if you're familiar with that. And this says that the change in value at a particular state over time, backwards in time, negative because we're propagating this backwards in time, is based off of what's called the Hamiltonian. And for those of you who's not familiar, this is essentially saying that I want to take my control and I want to minimize along gradients of my value function. I'd like to do gradient descent. However, I need to obey the laws of physics. I have a model that has some physical constraints to it. And so I look at the inner product between the dynamics of my model and the gradients of the value function and try to do gradient descent along that. So try to, given my model, to push as much as I can in negative directions of the value function. The disturbance, I assume, is doing the opposite and trying to do gradient ascent. So this takes care of our minimization over U and our maximization over D. I still have this min over time that I need to throw in there somewhere. And so we have one more additional thing, which is this minimization term. It takes more than a couple of seconds to explain the intuition of why this is a minimization over time, so I'll skip over that for now, but I'm happy to discuss that more offline. But long story short, we have our value function, we have our means of updating to get our value function. And in order to construct this now, we're going to grid up our state space and apply this update equation at every point in that grid at every instant in time for our time horizon. And this is what it looks like. So here, I'm propagating this cost function backwards in time to generate the value function. Let's say that I care about a time horizon of 10 seconds, so I'm going to stop it there. And this is my value function. Everywhere where this function is negative corresponds to initial states from which I'm able to achieve negative cost or able to get inside of the goal. So therefore, I care about everywhere where this value function is negative. So I'm going to slice it at 0 and flip it back over. And that is my reachable set. That is the set of states from which I am guaranteed to reach my goal despite worst case disturbances. So traditional Hamilton-Jacobi reachability analysis is very beautiful in many ways. It provides these hard safety guarantees and it provides control policies. And that comes from the fact that we now have this value function with these nice gradients that inform us of the direction that we need to apply our control in order to satisfy those guarantees. And so it has a built-in online controller. We have a lot of different toolboxes for using this, ranging from Python, MATLAB, C++, and we've applied it to many, many different applications. But it does struggle a lot in a few areas, and you may have picked up on them already. It struggles with complex models, and it struggles with uncertain environments. So let's go a little bit into what I mean by that. First, complex models. So we are doing dynamic programming. We are gridding up our state space, and we are applying this update equation at each point in that grid. That means for every additional state dimension I add to my system, I'm adding exponentially more grid points that I have to reason over. So very quickly, this becomes intractable for real systems. So often instead, you see things where instead of using the full dimensional quadcopter, you use like a 2D point mass that moves up and down. Or instead of a realistic model of a car, we use something that a cartoonish model that just has like X, Y position and an angle. Or instead of having trying to model the high dimensional human body, we instead assume that humans are just, probably double inverted pendulums. And this might not capture the full expression of how humans move. And therefore, a safety analysis done on this might not be that valid for the higher dimensional system. In terms of uncertain environments, we struggle with this as well. There are some ways in which it's really nice how reachability deals with uncertainty. One is the fact that we can incorporate in disturbances and be robust to them. But it does require these bounds on disturbances. I need to know what is the worst that the disturbance can do to my system. And that can either be very conservative, if I assume the worst to say that a hurricane could happen, or it could be unrealistic if you have bounds that are not actually true. And so when you find out that those uncertainties and disturbances are different than what you expected, recomputing this because of those computational challenges can be really difficult. We can handle obstacles. So here's an example of an obstacle. Here I have a cost function, the second one, that's high cost, positive inside the obstacle, and low cost or negative outside. I can even handle moving obstacles if I know how they're going to move. So if I knew ahead of time how this obstacle is going to move, I can actually incorporate that into my analysis. This is maybe my favorite video in terms of watching how it wraps like molasses around the obstacle, all coming from the math. And what we get in the end is now a reach avoid set. So the set of states for which I'm guaranteed to reach my goal while avoiding the obstacles. The problem is, like I said, I needed to know how that obstacle was going to move ahead of time. When we're trying to deal with things like navigating around humans, we can't necessarily assume full knowledge of their trajectory ahead of time. So that's what I mean by struggling with complex models in uncertain environments. So two approaches that I've taken to try to try to deal with this is system decomposition and warm start reachability analysis. The decomposition idea is very simple. It's just, if we have some high dimensional system, wouldn't it be great if we could kind of rip it apart, look at the lower dimensional subspaces, and then kind of smush it back together in such a way where we can say something about the full high dimensional system. So here's an example on a smaller system for explaining the idea. So here I have this little car model where my x position is a function of the speed and the angle. Y is also speed and angle. The angle changes with respect to rotational velocity, and the speed changes with respect to acceleration. If I look at how this model, the states depend on each other, okay, so x depends on v and theta. Y similarly depends on v and theta. And theta and v each depend on the inputs. It's unclear how I would be able to split this up and decompose it because we have these edges that cross and they're coupled. So we asked a pretty naive question, which was just, what if we do it anyway? What if I just break this down the middle, rip it apart, and try to analyze them separately? Clearly, you might be able to notice that we're missing some information now. And so we asked, well, why don't we replace that missing information with a worst case assumption over what that information might be? So assume here that the velocity will take on the worst possible value given what we are trying to do, and similarly with the angle. We now have two 2D systems, which is, when you're dealing with exponential scaling, a lot better than one 4D system. But we have introduced now an additional disturbance. The way we're going to combine these together is we're going to say that the value at a particular x, y, theta, and v is going to be the max or the worst case between the value of each one separately. A quick kind of visual sketch of the idea and the proof is that if we have some goal in our 4D space, I'm going to project that goal down onto the x, y, or x theta subsystem and the yv subsystem. I'm going to analyze those each separately in their 2D space and then lift them back up to the higher dimension. And then I'm going to take the max, or in this case, the intersection between the two. Now, my true reachable set might look something like this, but I know I'm guaranteed to have a conservative under approximation of that true set. And this is because we're introducing that disturbance that's working against us as we try to grow this set. So this is what it looks like on that actual system. I'm showing two 3D slices since we can't see in 4D. In green, I'm showing what it looks like for the full formulation. And then in purple, I'm showing the decoupled approximation. And here, we're able to get 20% of the volume in 1.5 minutes compared to the half a day that it took to do the full formulation. So if you look at the number of grid points and the scaling, the full formulation very quickly becomes intractable for us. Whereas using decoupled approximations, we can do this for higher and higher fidelity. And you'll see some examples of this on higher dimensional systems later in the talk. Okay, so I usually skim over this part, but since there were some questions ahead of the talk about this, there is a way in which we can sometimes get this back exactly. So we asked, why are we introducing this disturbance? Why not go ahead and put in the state and its input, do the same thing over here, and now you remove the disturbances from the system. You have two 3D systems now, but you have no disturbances. These are what we call self-contained subsystems. So x and y don't directly depend on each other, but x theta and v and y theta and v each do. We now will say, okay, in same setup, so here I'm showing 3D x, y, and theta. I'm going to project this down onto the x theta and y theta dimensions. Here's what it looks like when I project it back up. We're going to keep track of that intersection. And now I'm going to propagate each one of these independently and look at the intersection. So in blue, I'm showing the direct computation, and the hash marks, I'm showing the decomposed computation. And they match up exactly. And because we reduced this by a dimension, it was significantly faster. Note that this requires the self-contained subsystem formulation and some specifics about the problem setup itself in order to get those exact solutions. But it's exciting when we can do it. Any quick clarifying questions on the decomposition work? Okay, great. So now, oh, go ahead.
Sorry. Are you assuming that the controls are they're decoupled between the two subsystems? So if I have systems where you have decoupled control, if I have a system where the controls are not necessarily decoupled, are you assuming that this decomposition, can you guarantee that this decomposition would work for those subsystems?
You introduce additional conservativeness from this. So if you assume that your control affects both X and Y, for example, and your control is like a circle, 2 norm, you can decompose this by assuming a lower bounds on your control in the X dimensions and in the Y dimensions. For the coupling in general, for dealing with the fact that controls and also the virtual disturbances that we applied do in fact affect the other system. We've talked a bit about kind of doing an iterative version of this, where occasionally the systems are allowed to pass forward information about the other one, but in a kind of a sparser formulation, rather than having them completely decoupled. But we actually haven't fully explored this, so I'd be happy to chat more.
Mehdi has a question in the chat.
Yeah, just a very quick question. Like in practice, is having, say, 20% of the volume acceptable, or any thoughts on that?
Oh, yeah, great question. It depends. If it's something where it was totally intractable ahead of time, having any sort of space from which you can guarantee being able to attain your goals can be really good. In some cases, it might not be sufficient to only be able to recover 20%. And so it really depends a lot on the specifics of the problem formulation. There's a lot of details that I didn't go into here on the trade-offs between how to reduce conservativeness in some respects, that introduce conservativeness in other respects, and trying to find the optimal way of kind of ripping apart your system. And in general, there's a lot of analysis to still be done on how to do this intelligently. And again, I would love the opportunity to chat more about that.
Sure, thanks.
Okay, the second one is worm start analysis. The idea here is also very simple. It's just, sometimes we deal with changes in the autonomous system. Sometimes we deal with changes in external disturbances or changes in the behavior of other agents. Here, this is one of my favorite robot videos. It's a mall robot that's being terrorized by children and has to figure out how to deal with children separately from adults. And in these cases, you need to figure out how to update your safety analysis. And recomputing it entirely from scratch can be really painful computationally, as we saw. And so if there's a way that we can steal concepts from optimization, reinforcement learning in order to be able to warm start our analysis and be able to converge to the true solution, then that would be great. And we found that if you initialize with a value function that's overly optimistic, so if you assume that the world is great and it turns out the world's much worse, we can ensure guaranteed convergence to the correct solution. If instead you assume that the world is worse than it actually is, and you initialize with something overly conservative, we can guarantee that you won't be more conservative. You will make progress towards the true solution, but you may not be able to attain it completely. So you'll be less conservative than before. This was actually pushed further by my colleague, Jaime Fernandez-Fazak at Princeton. And he introduced a discount factor, just like in reinforcement learning, that ensures convergence to the true solution. Sometimes this discount factor can introduce some annoyances in the actual computation. So there's a little bit of trade-offs of when to use it and when not to. Again, happy to go into details if people are interested. But the exciting thing now is that we can now initialize safety analyses with best guesses or approximations, and then be able to converge to the true solution from there. So this is really nice for applying to safe learning. So here's a project in which we have this 10D nonlinear quadcopter model. Unfortunately, it's in simulation because of COVID, where it's flying this figure 8 and trying to track it. And you see that there's some unexpected wind disturbances that knock it off of course. And so it needs to be able to update its information about those disturbances. It's doing that here using Gaussian processes. And then based on those new disturbance bounds, update the safety analysis accordingly. And to be able to do that kind of in a way that's reasonable to use in real time. So the way that we tried to take this 10D system and make it so that we can actually update safety efficiently was by incorporating in some of these approaches. So first we did decomposition. So we took that 10D system and split it into two 4D and one 2D system. We then applied this warm starting, so where we updated from the previous solution rather than recomputing from scratch. And then we did now adaptive grids because we could start with a really rough approximation using a very coarse grid, and then now use that warm starting to initialize a finer resolution computation using a higher resolution grid. Here we were doing just very naive, coarse uniform grid, fine uniform grid. I think there's a lot that can be done there to improve things. But even just using these fairly naive approaches, we went from intractable, we couldn't do anything with a 10D system before, to the order of hours using the decomposition. In blue, I'm showing the initial computation, and in purple, I'm showing the updated computation. When we then added in warm starting, well, it still took forever to do the initial computation, but then updating it was much faster. When we did that, plus the adaptive grids, so we initialized with the very coarse and then refined it over time, we were able to reduce the time by quite a bit for both the initial computation and the update. So even just kind of these simple approaches are really helping improve the scalability of these techniques. This has been applied by my colleagues. So this is Andrea Baishi at Berkeley and Solmo Bansal at USC. Here they're doing a local version of this. So they have some control policy that they learned using a neural network controller. It's taking in a camera information about the environment, it's outputting the control it wants to apply, and they want to wrap this in safety by having this safe bound computed by reachability around the system. And they don't know the environment ahead of time, so as they discover more about the environment, they'd like to be able to update this safe bound and update the safe control accordingly. And they're doing a localized version of this that only updates in the areas where you have new information. So rather than updating across that whole uniform grid, they're only updating in the regions where they need to in order to update in that local area. And again, they found that this made the safety analysis actually tractable for doing it real time. I want to throw out just one more plug for my colleague Solmo Bansal's work. So he recently came out with this paper called Deep Reach, in which he showed that you can actually construct these value functions using neural networks if, rather than using ReLUs, you use sinusoidal neural networks. And so here, this is the ground truth safety function. So here in blue is safe and red is unsafe. ReLUs, you get this kind of piecewise thing that is especially bad because we care about those gradients of the value function in order to get our control. And so instead, using sinusoidal activation functions allows us to get this nicer, more realistic looking thing. And the cool part about this is that it totally boggles my mind in terms of changing the scalability. And here it scales now with the complexity, how weird looking that value function is, rather than the grid resolution. You lose hard guarantees though from this. But since it changes the scalability, we can maybe combine this together with the kind of rigorous warm starting solutions in order to locally update after an initial learning-based approximation. That was just a very quick plug. I'm happy to.
Sylvia, if you don't mind, someone has a question in the chat. I already answered from the response you provided to the mail yesterday. Basically, it's asking if the decomposition is going to work up to 100 DIMs.
And great question.
If there was a way.
And how much conservativeness?
Yeah, yes. So some of the things we touched upon yesterday, but yeah, it would be nice to hear from you directly.
Yes, absolutely. So the conservativeness is a really good question. We haven't fully explored this, but we need to do more analysis, but I can provide a little bit of intuition of how conservativeness would affect higher and higher dimensional systems. The first is just how many edges are you splitting when you're ripping this apart? The second is where are you introducing these virtual disturbances? So let's say I make X, the actual position X, a disturbance. Then every time I try to update my system, I allow an adversarial person to choose where physically my system is. So clearly that would have a really strong effect on the ability to have growth of the system. If instead it's something like acceleration, it's further down on that integrator chain, then changing the acceleration is really annoying, but it doesn't have quite as strong an effect as changing something like position. Similarly, when you rip this up, the bounds on that virtual disturbance matter. So for example, in the thing that I showed, one of my virtual disturbances was theta. And if you let theta then operate from minus pi to pi, then every time you're trying to get to your goal, theta can just flip you around and point you in the exact opposite direction. If instead you break this up and say, let's look at theta from minus pi to 0 and 0 to pi, then you can break that down a little bit more. So anyway, I could keep going. There's a lot of complicated factors that enter into where conservativeness comes in. And I think in general, it's a really interesting question of, given a really high dimensional system, what is the best way of splitting it up? One other quick comment is that each way of splitting it up independently provides you with a guaranteed under approximation. So if you have a lot of computers, and you can just set them all up and in each one rip it up in a different way and then smush all of those under approximations together, then you do still retain a true under approximation. And so there's also an approach in which maybe doing some things in parallel would be smart. Finally, the thing that I briefly mentioned of allowing some level of communication between the two decoupled systems or multiple decoupled systems, I think would also really improve the conservativeness. The long story short, I've done it up to, I think 12 dimensions. I have not tried further than that, but I would be happy to chat with people about trying to push this.
Follow-up question. So these 12D system, they're all Dublin-scale models?
They're mostly like quadcopter models and things like that, just because we fly quadcopters in the lab.
Okay.
But other ideas for different ones, I'd also be.
Okay. And Alex has a question in the chat.
Yeah.
Alex?
Hey. Thanks. My question is for like the smoothness of this gradient. What about if you like bounded the Lipschitz constant? Because there's pretty good techniques for doing that in deep learning, and I guess like if you're doing the sinusoidal thing, it's very conditioned on like how it chooses to saturate them or not saturate them.
Yeah. Yes, absolutely. And in general, the scaling the value function and kind of and renormalizing it can help a lot as well with dealing with these gradients. Again, happy to chat more in detail on that afterwards. But really, really good point. Yeah, in general, the gradients are important here. And so applying any tools and techniques that you all have in mind for being able to preserve those, I'd love to chat about. And I'm sure Solmel would like to as well. Okay, so the TLDR is that theory and tools for scalability can make safety analysis more tractable. So this is nice. But in most of these cases, you know, I was showing that we were getting to the order of like a few seconds for updating safety. If you're trying to generate real-time safe control, this still is not quite at the level where we can handle real-time navigation. So that motivated this project Fast Track. So the idea here is, you know, I just showed you how to do very slow and accurate planning. If I have a system, some obstacles, a goal, I can give you the optimal control to get to that goal despite disturbances, etc. In robotics, we often do fast but less accurate planning, where we have, you know, we abstract away the system, we very quickly generate a path to the goal, and then we try to track that. The issue is tracking that. We may not be able to track it exactly. We may not be robust to disturbances, and so we can't necessarily guarantee safety. So how do we kind of merge these two approaches? So in general, I'm very interested in the fact that humans have to deal with this on a daily basis. You know, we are high dimensional systems that need to operate in real time. And so there's a lot of work studying how humans navigate and make decisions in real time. And there's some theories that humans, you know, have a very simplified model. They use that simplified model for planning, and they have some notion of the uncertainty around that simplified model to map back to their high dimensional system. So when you're pouring your coffee, you don't plan every single path of your fingers. You plan with a simplified model that has a map back to the high dimensional system. So can we do a similar thing? Can we plan using the simplified model, but with some bound around that and some knowledge of how that maps back to what our high dimensional system should do? So the idea here is we'll plan using that very simple point mass, but with this bound, whereas we try to follow this plan, we know we'll stay within this bound. And I'll go into details of that if that doesn't make sense, don't worry. Here's kind of what we want to do. So here's a project with the Marco Pavone's group at Stanford, where we're planning in a new environment. We have this, I forget if it was, I think 7D maybe, plane that's trying to navigate through this environment. And it's planning using a lower dimensional system here in real time, and then trying to track that. And it has this bound around that. Two quick things to note. Again, we don't know the environment ahead of time, and therefore we don't have a nominal reference trajectory ahead of time. We need to generate that in real time. So here I'm showing those two kind of versions of our system, the very simple one and the higher dimensional one. And we're going to think of this as like two different entities. Essentially, we're going to call this the tracking agent and the planning agent. Here, just for the sake of visualization, since we see in 3D, I'm going to make our high dimensional system just a 3D version of that Dupin's car. And our low dimensional system will just be a point mass that directly controls velocity in X and Y. Now, thinking about the behavior of these two systems, our tracking agent is trying to track or pursue the planning agent. So I'm going to call it the pursuer. The planning agent, we don't know what it's going to do ahead of time, right? I might not even know the planning algorithm. I don't know the environment. So that's missing information. We're going to, again, replace that missing information with a worst case assumption over what it might do. And so in the worst case, this planning model is being as difficult as possible to track. It's actually trying to evade us. So we're going to call this the evader. I'm going to say, given this worst case situation where the planning is being as difficult as possible, what will be the largest relative distance over time? So what will be the maximum relative distance over time, which is equivalent to saying the worst possible tracking error over time, which will be my tracking error bound. So to compute this, I care about this relative distance. So I care about relative state, which means that I need to think about the relative dynamics between these two systems. So to do this, I'm going to imagine that my planning system's at the origin and look at the dynamics of my tracking system relative to that. So if I'm trying to get to the origin, what will be the dynamics of my system? Here it's pretty simple. We take those 3D dynamics and we subtract out those 3D dynamics. Now, with those relative dynamics, we're now going to define in the relative state space a cost function. This cost function is simply distance to the origin. Remember, the origin is where the planning agent is. So I care about minimizing the distance, so minimizing the cost to the origin. So I care about doing that, but what I want to capture is going to be the maximum cost, the worst that I possibly do in the optimal trajectories over time to give me that tracking error bound. So my value is going to capture the maximum cost of trajectories over time. Here I'm going to put in, again, that trajectory notation, where the tracking agent is trying to minimize this cost, trying to do gradient descent. Planning agent, again, assume worst case, is trying to maximize this cost. So we have our inf soup in here. This should look familiar now for our value function. We throw this into our reachability analysis, and we propagate this, and we get something like this. This didn't mean very much to me when I saw it for the first time, and so I needed to break it down and think about what exactly is going on in this computation. So let's take a look at that again. Here I'm going to take different slices of this cost function, and I'm showing these slices here in 2D, so in X and Y. The true slices in 3D would be X, Y, and theta. You see it looks like a cylinder because I only define my cost in X and Y. I don't really care about the relative angle, and so it's constant across theta. So you can think of, oh, sorry, go ahead.
Sorry to interrupt. So like the cost function you're using to solve this, it's not the exact value function in the inf soup function, in the inf soup that you pose. You're using the viscosity, the numerical solution to the AJ problem, right?
Yes, yes. So
okay.
We're using the viscosity solution. So yeah, there can be, so you're pointing to that fact that there can be sometimes discontinuities where the gradient isn't defined. And so you can look at the viscosity solution in order to look at subgradients and supergradients in order to maintain
cool.
Yes, I don't normally people don't pick up on that. So you can think of these slices as candidate tracking error bounds. So, you know, if I look at these and I think about the fact that my tracking system has this kind of fixed radius of curvature, it's maximum turning rate that it can do. And I think of my planning agent at the origin of each of these candidate tracking error bounds. I can ask, where can I put my tracking system such that it stays within this bound? Well, here, if I put it over here, it's going to have to exit the bound in order to come back in. So that's not a valid state. I need to kind of scooch it back so that it just barely stays inside. If I start it over here, well, that's fine, as long as it can turn more sharply than the radius of curvature of the bound. And if I start it here, well, that's fine, it just goes into the bound. So I would expect the set to look something like this, as the set of states I can start in such that I can stay inside of this bound. Here, looking at a smaller set, you might imagine that we need to scooch this back a little further. So you have a slightly smaller set. And eventually you reach a slice where it's so small that even if you start back out here, you're going to have to exit the bound in order to come back in. And so there will be no slice that works there. So let's go ahead and run this again, given that intuition, and see what happens. You see the value function changing over time, and you see it pulling away from the right as we expected. And eventually, in this case, the value function converges. And so you see now that there's many different slices I could have taken here, for which if I start in this purple slice, I'm guaranteed to stay within the blue bound. If I start in this red slice, I'm guaranteed to stay inside of this larger bound. In fact, because it converged, for those of you who may have noticed, this is actually stronger. If I start in the red slice, I will be guaranteed to stay in the red slice. This corkscrew is what it actually looks like in 3D. So this is, you know, if I took this slice, which is at an angle of theta with the plane facing to the right, and I stacked it and rotated it across theta, you end up with this nice corkscrew, a screw shape. So this is my tracking error bound. So let me reiterate. We have this value function. I'm going to take like the smallest slice because typically we care about minimizing error. So I'd like to find the kind of tightest bound that I can stay within. I'm going to take the smallest slice that I can and look at what that looks like. This is now the tracking error bound in the 3D space. Now, the planning system doesn't know about 3D space. It only knows about X and Y. And so I need to project this down onto X and Y. And this is what it looks like for the planning system. It has this donut shape because, you know, the planning agent's at the origin, and no matter where it tries to go, the tightest bound that the tracking agent can have around it is one which is doing donuts around the planning agent. This is apparently how wolves track their prey. So we had our tracking system model, our planning system model. We got our relative dynamics from that. From that, we get our tracking error bound that we're going to use for our online planning algorithm, and also a tracking controller that we'll use for online control, because the gradients of this function are going to tell me the optimal control for my system to chase that planning agent. So this is what it looks like online. I have some unknown obstacles, a goal, and I start with figuring out where my tracking system is. Based on this, I'm going to initialize where my planning algorithm is going to start from. Let's say it starts from right there. I'm going to put that state into my path or trajectory planner. Whatever it is that you're using in order to generate this, it's a black box to me. I don't care. All I care about is the fact that it's going to take in the environment, locally sensed environment, augment them by the tracking error bound, and then use that augmented environment to output wherever it wants to go next. Now, based on the relative distance, the relative state between where I am and where that is, I just ask my tracking controller, how do I chase this lower dimensional plan? And I apply that tracking control. Now note that I might not be able to track it exactly, but the delta here will never be greater than this bound. So by augmenting obstacles, I can be sure that I won't violate the true obstacles. So we then just repeat, we plan, and then we chase that plan until we reach the goal. The important thing to note on this slide is that this is really a very lightweight wrapper around whatever path or trajectory planner you're already using. All we're asking is that you augment obstacles, which we often do in robotics anyway, but this time by like a rigorously computed bound. And that you take the next planning state and look at the relative state and use this lookup control of something you've pre-computed of how to best chase that state. And so it's a very lightweight wrapper that goes around whatever it is that you're already doing for your path and trajectory planner. Here's the first simulation that we ever did. So here we have this 10D near hover quadcopter model and the 3D point mass model. Even doing the relative dynamics in the pre-computation here would have been intractable, but we're going to apply that decomposition work to look at the X, Y, and Z subsystems. We then get a 10D bound that we project down onto 3D, and that's what you see here. And so here are unsensed obstacles. I'm going to plan using RRT. You see the green dot is my plan. As I sense obstacles, they turn red, and I replan in a very simple way. And then I just chase that plan with my 10D quadcopter model by just looking up the relative state and the control I should use to chase it. And note that even when the planning agent does a sharp 180, like it did here, we're able to stay inside of that bound because we assumed worst possible planning behavior. So doing that, we're able to just generate this in real time safely for this 10D system to get to our goal. This has been applied in a bunch of different labs. Here's one lab where they did this virtual reality thing of your drones going through hoops and stuff, and they're using fast track as the underlying controller. Here's that project with Stanford, in which they're actually using sum of squares optimization instead of reachability in order to compute this, because we wanted to do a scalability comparison. And here's a project in which the people trained a classifier over the optimal tracking control in order to, again, push the scalability of this. So the point here is that fast track allows us to kind of just robustify fast and simple planning algorithms. So it doesn't ask anything at all of the planning algorithm. Planning algorithm has no knowledge at all of the high dimensional system. It's just navigating through its space. And we're just doing our best to keep up with it. And given that total separation of the planning and the safety, this is a very modular approach to kind of robustify those algorithms. And that's why I think it's been used in so many different labs, is because you just throw this on top of it without having to adjust your planning at all. Now, that advantage comes with disadvantages. So because we're assuming worst case behavior over this, we assume that, for example, our system can't squeeze between these two obstacles, because if the planning algorithm is trying to mess with us and does a quick 180 right here, we might end up crashing while trying to chase it. In reality, our planning agent might not actually be adversarial, might not actually be trying to work against us. And so if you have a case in which you can communicate with the planning algorithm, you can reduce this conservativeness by a lot. Here's an example from some colleagues at Michigan. So here they implemented fast track. So you see here in just such a way that you can't actually get to your goal because of that tracking error bound. Whereas instead, if you put some limitations on what your planning algorithm can do and have some communication between the planning and the tracking, then you can squeeze between these obstacles. And so it's nice that we removed the need of the planning algorithm to pay attention, but we end up with this trade-off. So I was trying to figure out how to deal with this. And at the time I was reading this book, Thinking Fast and Slow by Daniel Kahneman, in which he asserts that humans operate as a hybrid system that switches between a fast, error-prone mode and kind of a slower, more rigorous mode. And he calls them System 1, which is fast, and System 2, which is slow. And I wanted to know if we could apply that to fast track. If we could have our high-dimensional system, but then have like a suite of lower-dimensional planning models. In the simplest case, let's assume it's literally the same one, but one is literally faster than the other. One can move at a velocity that's twice the other one. That would mean that in one case, you're planning with me. I'm pretty slow, but it's easy to keep up with me. And so the error bound would be pretty tight, but we would move slowly through the environment. In the other case, let's say you're planning with Usain Bolt, much faster than I am, but it's hard to keep up with him. And so you would end up with a much larger error bound. That means that now you have options as you're planning. You can ask, well, if this point is in collision for my fast mode, If I was willing to switch into the slow mode, would it still be in collision? And if not, you can actually add that into your tree and do this switching between moving quickly through open environments and slowly and more carefully through tight environments. Note that switching safely is non-trivial. We also use some reachability for that, but given that, we have a proof of guaranteed safety throughout the process. So here's an example of that, where we do this meta planning. Here you have this really big bound as we move quickly through the environment. But as it samples points that are in collision, it automatically decides when to switch into, you know, tighter and tighter bounds and move more slowly in order to navigate through that environment. So here again, we're allowing the planning algorithm to do whatever it wants, but conditioned on staying within the model and the constraints that it has.
So someone asked a question in the chat.
Sure. As it has some similarity with RRT star. Yes, we're using RRT star as the underlying planning algorithm for the low dimensional system. Oh, wait, there's
optimality proof or guarantee of the path computed.
So again, the low dimensional path is just whatever, if you're using model predictive control, RRT star, A star, it's going to have the same constraints as whatever the lower dimensional system is that you're using for planning. But given that, we have guarantees on the high dimensional system's ability to be able to stay safe while tracking that plan. Maybe you're hinting to the fact that you could have some feasibility issues where, let's say you go down an alley that ends up being blocked off and you can't get out. There's actually a paper that some of my colleagues did of being able to introduce recursive feasibility by putting some more constraints on the planning algorithm. But it's, again, this trade-off between how much you want to constrain the planning algorithm versus how much freedom you want to give and just have like this modular wrapper around it. Given the time, I'm going to kind of power through the last and just very quickly mention this last area. So this is dealing with the fact that in the real world, we don't have just these static obstacles. Instead, we have humans. And, you know, if I'm trying to get to a goal and I have a human there, like I said, if I know exactly how that human's going to move, I'm good to go. I just incorporate that into this analysis. I get my reach avoid set, and then I move. Humans don't behave this way, unfortunately. And so traditionally in my area, we assume that we don't know what's going to happen with humans or other agents. Again, we assume the worst case. So we assume that the human might go anywhere at any time, which means that we're essentially looking at this expanding obstacle of all the places they might go. When I put this expanding obstacle into my analysis, very quickly you end up with these super conservative results where maybe there's only a tiny region from where you can reach your goal, or you might not be able to reach your goal at all. So how do we trade off between overly optimistic and overly conservative? So we end up using, again, this cognitive science-based approach. We use a noisily rational Boltzmann model that adapts how confident it is in this model. So we have a probabilistic distribution, and we reason over, sorry, I'm going very quickly over this, but I'm happy to talk more later, the variance of this distribution. And so when our model of the human matches with the model, with the human's actions, then we have a very tight variance over this prediction. When the human's not behaving according to our model, then rather than trying to update this model or assuming, you know, that the human is being irrational, we instead just increase the variance of this distribution, eventually leading to what's called a full forward reachable set, back to saying that the human could go anywhere at any time. Adapting this confidence allows us to very quickly online use super simple, super dumb models of how humans work and just reason over how confused we are with them. So here's one in which I'm moving around this unmodeled obstacle, and the distribution spreads out as I'm doing it. Oh, sorry, this is the failure case. It doesn't in this case, and we end up in this terrible collision. So if instead we apply this confidence thing, where we change the variance of our distribution when the human is behaving in this weird way, then you see that the robot actually takes this wider berth around me. This works very well for things like multi-agent environments where we don't have a model showing that humans have to move around each other. We assume silly things like humans walk through each other and don't interact at all. But when the humans actually do interact, The robot then has to get confused, have this wider distribution over where the human might go, and then move around us. So this is what it looks like in the actual experiment. Sorry, I'm moving so fast. But if I show what's going on under the hood, here's the two humans and their predictions. As we move towards our goals, these predictions start tightening up. Or at least they do for me. Jaime's dancing the entire time, so it doesn't really for him. But then when we move around each other, you see that distribution spreads out, and this robot actually has to wait a minute in order to replan around us. There's a lot of exciting projects related to this that I'd like to talk about, but I'm going to try to power through this so we can get to questions. In terms of active areas that I'm really excited about, continuing pushing on the safe learning and learning safely. There's a project with a NASA engineer of trying to apply this safe learning approach to some of their vertical takeoff and landing vehicles. I'm super excited about the connection between reachability analysis and this other subfield called control barrier functions. We have a paper coming out in CDC showing the theoretical connections between the two and how we can smush tools from each approach together. We have some approaches of trying to incorporate the safe learning stuff into constraints for online Q learning. We're trying to go beyond safety, thinking about safety as just avoiding collisions, and instead thinking about safety for things like surgical robots, where instead you have to reason about how willing you are to move aside tissue and push against things and try to do that safe exploration in a rigorous way. And then continuing to push on this scalable navigation multi-agent environments by reasoning about, similarly to how we did the meta planning for the fast track, can we switch between different fidelities of human models as needed online based on our computational constraints? Oh, I'm sorry, I know that was a lot. Sorry, I just speed up near the end, but let me just, here's the areas, here's my website and my email. I'd love to talk more, and I can also stick around for a few minutes now.
Yeah, obviously it's a very exciting area of research. Thanks for the didactic talk. If anybody has questions, now would be a good time to ask. We have just 2 minutes left, but Sylvia's promised to stay way long before that. Kim Bio.
Yeah, I'm happy to stay.
Yeah, so Kim Bio, I'm sorry if I'm not pronouncing it correctly. If you want to ask a question.
Thank you so much. It's a really exciting and inspiring talk. So I'm a PhD student at Cambridge, currently working as a research intern at Microsoft Cambridge Research. So yes, I think some of your talk and the content is very inspiring and related to my PhD topic because I'm doing multi-robot research. For example, probably I missed it. In the safety human-centered robotics, are you using Gaussians or something to modeling the uncertainty of the human motions in the last slides? When you
we do a Bayesian update over this distribution over what variance we want to apply, this beta term that controls the variance. And so we look at the actions that the human's currently taking and the actions that we expect to take, and then we do this Bayesian update based on that.
Okay.
I'd be happy if you send me an email. I can send you the papers and we can have follow-up conversations.
Okay, sure, yes, sure, yes.
Yeah.
Oh,
and thank you for. Let me make a note of this paper that you just sent me.
Yeah, I'll send it over to you after the talk.
Okay, great.
Mehdi has a question as well.
Okay, I don't know how much time do we have. So first of all, thanks, Sylvia. I really love the visualizations, especially. I have a question. So this reachability analysis is based on the worst case scenario as well as accessing the optimal policy. You discussed how to relax this worst case scenario in different ways, but how about if the optimal policy is not available, say due to partial observability or whatever other reasons? Can we add that in terms of, I don't know, additional disturbances or something like that and bound the outputs? Any thoughts on that direction?
Yeah, okay. Lots of good questions that you're bringing up. First, in terms of dealing with worst case, there's also different approaches of dealing with stochastic disturbances and dealing with using CVAR, using a risk-based version rather than worst case or just expected. It adds in a lot more computational complexity, and so there's some challenges there. Your question on the optimal policy, when the optimal policy is not available. I like your idea of introducing other sorts of disturbances into it. I think that we could absolutely do that. There's also interesting questions of, maybe you don't always need or want to apply the optimal policy, especially for safety. Maybe you don't need to go in the exact opposite direction of the obstacle. It's sufficient to just do anything that has a negative Hamiltonian, anything that will do some sort of gradient descent, even if it's not the strongest gradient descent. There's some work that has been done by this by my colleagues Mo Chen at Simon Fraser University, Karen Lung at University of Washington, and Marco Pavoni at Stanford. But there's still a lot, I think, that can be done of asking, can we relax the need for optimality? When do we not want to apply the minimum time action? And that, I think, is a pretty underexplored question. So I'd love to chat more.
Sure.
And Ivan has a question as well.
Yeah, thank you again for the inspiring talk. Brief context and question. You mentioned a lot of really great trade-offs, and just from the mathematical modeling side of things, where do you feel are some of the main bottlenecks or areas of research that would help clear up some of these things?
Oh, that's such a good question. One thing I'm sure many people here have thought about this, but I'm still assuming that I have a model of my system. I'm still assuming I maybe have some uncertainties that I can introduce in that, but I still assume some general form of it. And in particular, I assume that I know the dimensionality of it, like I know the states that apply to this. If I'm applying my safety analysis online and I realize that that's insufficient, that the model of my system does not capture everything that I need to, identifying that and being able to reason about what additional, like brand new dimensions, new states I need to incorporate into that is something that I really don't know how to do. I know that there's some research trying to explore this, but it's challenging, I think. There's kind of a similar, oh, sorry, go ahead.
Just a little interruption. I just want to say, like, if you feel like leaving, now would be a good time. If you don't have any questions, but like, I'm going to hang out here with Sylvia. If anybody has a question or something, feel free to. She's promised to be available for 30 minutes, right?
Yeah. Okay.
Yeah. So yeah.
And then I mentioned before trying to deal with disturbances in a more a stochastic way, adding in state estimation and uncertainty, adding in partial observability, all these types of things complicate this even further. And so I think that there's a lot of questions about how to introduce these more realistic scenarios in which you don't have all information about your states and whatnot in a way that's still tractable. There's a lot of other things I can complain about the field, so I could go on for a long time about this. So I'd be happy to chat more at any time.
Thank you.
Kim Bio, are you still raising your hand? Kim Bio, I guess.
I don't have more questions. Yeah, thank you so much.
Okay, cool. Yeah, thanks. Thanks a lot, Sylvia, for coming. I learned a lot from your papers, and then even more so from your talk today. Yeah, lots of interesting questions, and I assume people will be following up, and I will be following up as well. So yeah, thanks.
Yeah. Please do, and thank you so much for the opportunity to chat with you all.
Yeah, I see a lot of people applauding in the chat. So yeah, cool.
Okay, great. Have a good evening or day, whatever time zone you're in. Bye.
Yeah, we'll catch up later.